Okay. So my research was on photodissociation of methyl iodide. So to start off, photodissociation is a chemical reaction where a compound is broken down through the use of light. So the photons in the light provide the energy used to break the bonds in the compound. Methyl iodide was the molecule that was simulated in Matlab. It's a simple molecule that works well for this type of research. And the goal of the research was to use a simulation in Matlab and study how altering the length of time between two pulses of photo energy affect the properties of the dissociation between methyl and iodide. The methods used in Matlab, first of all, the initial wave function is calculated through that expression. It is the combination of electronic and nuclear wave functions with this part representing the electronic portion and the X not X1 representing the nuclear portion, with 0 being the ground state, 1 being first excited state, second being second, and so on. And X0, X1, they represent the wave function for each state. The Hamiltonian operator is calculated with this equation. Here's the momentum portion, which was kept constant throughout the simulation. And the potential energy surfaces for each state are calculated via this part of the expression with V0, again, V0, V1 representing each state, the electron. And with going into more detail, each parameter is calculated with this equation. And here are more the methods that are used to simulate the pulses of energy. So this is just the evolution operator of each wave function, but at each time of the laser pulse, it is calculated with this equation. Wave function experiences an additional pattern of evolution. And with each pulse, it's going to change the parameter from 0 to pi to 2 pi to 3 pi. And at 0, 2 pi, so every 2 pi, it's going to be in the original state, so the ground state, and each consecutive pulse will add a pi, and in pi, 3 pi, 5 pi, and so on, it will go to the excited state. Here's the simulation window, the main window that you're seeing as the simulation takes place. Alpha, well, I can just point them out. This black one is the ground state. Red is the first excited state. Green is the second and third. Those are the potential energy surfaces for each one. Probability distributions. This is if no pulses were performed. The black one is a combination of all of the probability distributions, as you can see through that equation. The green is for the second excited state probability distribution, and the blue is for the third. So after finishing a simulation, it's it brings out this figure that is the bond length plotted as a function of time in femtoseconds. And for the research, I decided to break up the pulses in delays of multiples of 10. So the first pulse would go, then wait 10 femtoseconds, then the second pulse would, and then 0 to 20, 0 to 30, and so on. And I did 6 of those tests. And here are the figures that resulted. So as you can see, with shorter delays in the pulse, well, I should say, first of all, this represents the total probability distribution in the earlier slide. It's this one here. You can see how near the end it breaks into 2 distinct distributions. You can see that in each of these graphs. And that happens sooner than later if the delay is a shorter amount of time. And you can also see that the slope decreases due to the increased time that the experiment has to take place. And I have some videos of the simulation windows as it is going. So here's 10 seconds, a 10-second delay. As you can see, right when the second pulse is acted, is simulated, the relative distribution drops energy level, and the distribution in the second excited state goes to the ground state. So that's that adding a pi and changing the state. So that's at 10, and compare it to a 30 femtosecond delay. So that's after 1 pulse. Then you'll see once the timer reaches 0, the second pulse. Okay. You can see it goes to the ground state. And the relative distribution didn't drop as far as it did in this 10 femtosecond delay. So there's less of a change in energy. And you can see it's about between 6 and 7 atomic units is the difference is the bond length. Then we can compare to 60 femtoseconds. I'll just skip ahead. It starts breaking into the 2 distributions much later when the pulse is shot into it at a later time, which we saw in the earlier figures. So, in conclusion, the earlier the second pulse is administered, the closer the CI bond is to equilibrium length, and the lower the total energy of the relative probability distribution. And the later the second pulse is administered, the further the bonds are, or the further the radicals are departed, and the higher the total energy. And it's obviously useful in actual laboratory testing to use a simulation like this before you do anything.
Okay, please join me. Anyone wanted to ask questions today from our session?
I have a question.
Yes, please, Dr. Han.
So yeah, I guess I'm just confused about the laser pulses.
Mm-hmm.
So I guess you have 2 laser pulses, right? So the first one, the first one is used to promote electrons from ground state to excited state, right?
Yep.
And it seems your second pulse is just to use to stimulate the emission. Is that right?
Yep. That's all it's for. Yep.
Okay.
Does it answer the question?
Yes.
Okay, thank you. There was, please stay here. We have another question. I will deliver the microphone.
It was on one of your previous slide, like the figure with the blue figures.
Okay.
What does it mean when the probability distribution split? Why does it do that?
It's
Just wait. Online visitors will not hear without a microphone or TV screen.
well, let me think about it for a second. It's just as the reaction goes on longer, the probability of the electron being in either the third state or the ground state is going to be closer to 100. I'm pretty sure.
Does that answer your question?
Yeah, I think so.
Yeah, it was a great question. So I interpret it as each of the potential energy surface controls development of the bond lengths with certain speed. And if there is a superposition of more than one, then there is a splitting.
Yeah.
Okay.
So on these figures you're showing right now, on the bottom 4, you have a black line through them.
Yeah, I guess.
Does that have any significance?
It was more to compare. So at 20 seconds, it goes up to 40. So I decided to compare what each graph would look like at that 40 seconds. And like I was saying, the earlier or the smaller the delay, the earlier it breaks into those two distributions. So it's just to kind of visualize that better. No, it's not a time there. I just chose that.
So you have 2 pulses like you were discussing with Yulin. So what it is, the first pulse is at 0 and the second pulse is whatever that time listed is?
Yep, exactly. So 30, 40, yep.
Okay.